Alright, today we're going to talk a little bit about resistive inductive series circuits. When a pure resistive load is connected to an AC circuit, the voltage and current are in phase with each other. When a pure inductive load is connected to an AC circuit, the voltage and current are 90 degrees out of phase with each other. When a circuit contains both resistance and inductance, the voltage and current will be out of phase with each other by some amount between 0 and 90 degrees. This is just a little important piece of info. The exact amount of phase angle difference is determined by the ratio of resistance to inductance. Impedance. Impedance is defined as a measure of the part of the circuit that impedes or hinders the flow of current. It is measured in ohms and is represented by the letter Z. We learned that last module. In a series circuit, the total resistance is equal to the sum of the individual resistors. We know that from DC. So, looking at this would be a resistive inductive series circuit. So we're just going to draw out an example here. So for this one, we have 240 volts total. We have inductive reactance of 40 ohms. And we have a resistance on this resistor of 30 ohms. And these are going to be asking you to find a lot, so it's going to ask you to find like current total, impedance, VA, power factor, ER, I sub R, which is just volts of that resistor, and current of that resistor, and then watts, inductance, voltage of that inductor, current of that inductor, and VARs of that inductor. So these are going to be asking you a lot more questions, and you're just going to have to work through them with the formulas that you're given. So this is just an example of what one may look like. So vector addition. So in a series circuit, the total resistance is equal to the sum of the individual resistors. We know that. That's true in DC and in AC. But in like an instance like the one I just drew, in this one, the total impedance, which is represented by Z, is the sum of the resistance and the inductive reactance. So it would first appear that the sum of these two quantities should be 70 ohms, because that would just be 30 and 40 added up, right? So you would think, okay, we just have a 70 ohm circuit. But the resistive part of the circuit and the reactive part of the circuit are out of phase with each other. You have to remember that. So they are out of phase with each other by 90 degrees. So you can't just add those two. So we're going to have to find these quantities using vector addition. And how we do that is we look at it like this. We look at, let's say we have a triangle up here. On this side, we have inductive reactance. This side, we have resistance. And this side, we have impedance. Okay? So, inductive reactance, resistance, impedance. The resistive and inductive reactance form the two legs of the right triangle, and the impedance is the hypotenuse. The total impedance can be calculated using this formula. So we've got Z equals R squared plus X sub L squared. So that's just going to be your impedance your resistance, and your inductive reactance. If you don't learn anything else, you need to learn what symbolizes everything. So you need to know that XL symbolizes inductive reactance. You need to know that R obviously symbolizes resistance and Z is impedance. You need to know what these things stand for so you can find the right formula to work these out. Because I'm not going to keep formulas from you. You can find the formulas on the internet, in your book, wherever, but you need to know what these stand for. So, how we work that out is, remember we had 30 ohms as the resistance and 40 ohms as the inductance. So, all we would do is Z is going to equal your 30 ohms, because that's your resistance, squared, plus your 40 ohms, because that is your inductive reactance squared. And 30 squared is 900 ohms. Oh my goodness. There we go. 900 ohms plus 1600 ohms. So you're going to come out to have, I forgot that. You're going to have 2500, because 900 plus 16 is 2500 ohms. And your total is going to come out to 50 ohms, and that's going to be your answer. So, instead of adding these two together, we cannot do that. Why can we not do that? They're out of phase by 90 degrees. So that's why we draw a 90-degree triangle. And they're out of phase by 90 degrees. So you'd find your impedance using vector addition. Alright, total current. We know that for series circuits, the current must be the same throughout the whole circuit. This is also the same for resistive inductive series circuits. Remember that impedance can take the place of the R in the Ohm's law formula. And so total current can be found by dividing the total voltage by the impedance. So it can take the place of the R in the Ohm's law formula. So we know Ohm's law is E over I times R. We know that. So we could simply just say E over I times Z. Impedance can take place of the R in Ohm's law formula. So if you wanted to find the current total, you would just do E total divided by impedance. So say you're given 240 volts and 50 ohms that we just found. Your current total would equal 4.8 amps. I know I'm writing over here where you can't even see. It would equal 4.8 amps. And that would be your answer. Voltage drop across a resistor. So, it can be calculated using the formula I sub R times R equals E sub R. Voltage dropped across a resistor is in phase with the current. Voltage dropped across the inductor is 90 degrees out of phase with the current. So across the resistor, in phase with current. Across the inductor, 90 degrees out of phase with the current. So if we can use this formula right here to find the voltage drop across the resistor. So you would just use the voltage of that resistor, the current of that resistor, times the resistance. So if you know you got 4.8 amps going through that resistor times the resistance of that resistor, you would come out with a voltage drop of 144 volts. You should remember that a little bit from DC, how you get the voltage drop of stuff. Alright. So the resistive quantity that is measured in ohms is resistance. Impedance and inductive reactance of a circuit were known. They could be used with the following formula to find the circuit resistance. So let's just write that down too. So if you already know impedance and inductive reactance, then you can find the circuit resistance. So circuit resistance, change the color, would be equal to, what does these stand for? It stands for impedance squared minus inductive reactance squared. So all these formulas start going together. I keep writing it over here where you can't see it, but it is this. Sorry, I keep forgetting that you can't see behind my head. Squared minus XL squared. So a lot of these formulas you're going to find in your book start looking like one another. Watts. So true power, which is represented by P for the circuit, can be calculated by using any of the Watts formulas or pure resistive parts of the circuit. So those formulas are going to be looking like what we already know, which would be volts times current of that resistor. So we would have 144 volts times 4.8 amps. This is stuff we've already found. So true power would be 691.2 watts. Inductance. So we should know what the inductance formula is from last module. So just as a refresher, the inductance formula is X sub L, which stands for inductive reactance, 2 pi F. So we know that this is inductive reactance. We know that's just 2. Pi is 3.14, and that is frequency. Okay? And frequency is measured in hertz. Alright. So, inductive reactance is measured in henries. Alright, so moving on. We know how to calculate inductance, so we're not going to go over that too much. The voltage drop across the inductor. So this is going to be the formula for that. So L stands for inductance, right? So anytime we see an E with a sub L or E sub R, E sub T, we would know that that means voltage total, voltage of that resistor, or in this case, voltage of the inductor, okay? So E remains the same. That stands for voltage. It's just the change of the sub L, sub T, sub R, whatever it's subbing, that's what it stands for. So voltage of the inductor is what we're looking for right now. So E sub L So we're looking for voltage of that inductor. So we're going to be using the current of that inductor times the inductive reactance. Okay, so for example, if we are looking for this and we know that the current of that inductor is 4.8 amps, and we know that the inductive reactance is 40 ohms, then your voltage drop across the inductor is going to be 192 volts. All right. Reactive power. So, reactive power is measured in VARs. We went over that last chapter 2, and that stands for volts, amperes, reactive. So, VARs represents volts and amperes that are 90 degrees out of phase with each other, such as the voltage dropped across the inductor and the current flowing through the inductor. So, those are 90 degrees out of phase with each other. So, looking at it, we're going to be looking at different formulas. The formula you would use in this case would be VARs equals I sub L squared times, this should be sub L, inductor reactance, with it times blue. So that would be the formula you would use to figure out the current series circuit we're working on. But now, in some of these cases, as just a reminder, because I'm not going to ask you to memorize these formulas are hard to memorize. So on pages in your textbook, 933 and 944, 933 and 934, all these formulas are on those pages. You just have to know which letter represents what you're looking for. So if you know that XL equals inductive reactance, if you know that L equals inductance, if you know what VAR stands for, if you know what all these letters symbolize, then you can know how to use those formulas. So once again, page 933 and 934, for the people that actually pay attention to the videos, there is a little cheat for you. You'll know where the formulas are and where you can look them up at in your book. They're every single one of them that you need. So no matter what information you're given, you can find a formula to work a circuit out if you look on page 933 and 934. Moving on to apparent power. It's measured in volt amperes, which is symbolized by VA. And it's called apparent power because it is the value that would be found if a voltmeter and ammeter were used to measure the circuit voltage and current, and then those values were multiplied together. So, let's see. Once again, all these formulas, the formula that you would use in the current circuit we're using would be VA equals E sub T times I sub T. But you could find this different ways. You could use VA equals, depending on what information you know, you could use watt squared plus VARs squared, all square rooted. If you know those, if you know VA but you don't know, say, VARs, if you wanted to find VARs, you could look at, it's just flip-flopping these formulas. So you could use VA squared plus, minus P squared. If you wanted to know P, which is watts, you could use VA squared minus VAR squared. So just flip-flop these formulas around. Sometimes they're easy, sometimes they're a little bit more difficult. But if you use those pages in the book and know what you're looking for, it becomes a lot easier. Power factor. Power factor, represented by PF, is the ratio of the true power to the apparent power. It can be calculated by dividing the voltage drop across the resistor by the total circuit voltage, by dividing resistance by impedance, or by dividing watts by volt amperes. So you could use this formula. You could use this formula. Or you could use this formula. I don't like the 2F's. So there's 3 different formulas you can use to find power factor depending on what you're given in the problem. Alright. Moving on to angle theta. Angle theta is the angular displacement where the voltage and current are out of phase with each other. So just looking at what angle theta actually is, we will draw a 90-degree triangle again. And down here we have true power. So we're going to have the watts down here. And just say our watts equals 691.2. That's true power. Watts is true power. And then we'll have reactive power up here, which is VARs. And that's equal to 691.2. So then we have apparent power, VA. And that's equal to 1152. So this angle in between here is what we're looking for. So that is your angle theta. The angle in between the bottom leg and the hypotenuse. Alright. So that's going to be the relationship of true power to apparent power. So true power to apparent power. Because we know that true power equals P, which equals watts, right? And we know that apparent power equals VA. And so, yeah. Apparent power equals VA. And that is going to be what apparent power stands for. And there's multiple ways you can determine angle theta. Once again, there's a bunch of formulas you can use. But if you wanted to calculate this one, it is going to be the cosine of watts divided by volt amperes. So watts divided by volt amperes is also the power factor. Therefore, the cosine of angle theta is the power factor. So if you wanted to do, I don't know if you remember SOHCAHTOA, but you can use this to work on your triangles. I'm not going to work that one out just because you can Google this on how to use SOHCAHTOA. But when you're trying to find the angle theta, you can use SOHCAHTOA in order to find that. And we're just going to go over a little summary of this chapter. So, we know that in a pure resistive circuit, the voltage and current are in phase with each other. So we know that. So, pure resistive equals voltage and current in phase. Okay. So, in a pure inductive, the voltage and current are 90 degrees out of phase with each other. So, 90 degrees out of phase. Alright. In a resistive inductive series circuit, the voltage and current will be out of phase with each other by some value between 0 and 90 degrees. The amount the voltage and current are out of phase with each other is determined by the ratio of resistance to inductance. So we need to know that resistance to inductance ratio determines phase. Okay? Total circuit values include total voltage, which is E sub t, total current, which is I sub t, and volt amperes, and impedance. Volt amperes is VA, which is apparent power, and impedance is Z. Pure resistive values include voltage drop across the resistor, which is E sub R, current flow through the resistor, which is I sub R, resistance, which is just R, and watts, which is P. Pure inductive values include inductance of the inductor, L, voltage drop across the inductor, which is E sub L, current through the inductor, which is I sub L, and inductive reactance, which is XL, and inductive VARs, which is VARs sub L. Angle theta measures the phase angle difference between the applied voltage and the total circuit current. So we'll write that one down. Angle theta measures the phase angle difference between applied voltage and total circuit current. So voltage and current. All right. The cosine of angle theta is equal to PF, which stands for power factor. So, if you know the power factor, you know the cosine of angle theta is equal to the power factor. And last one, power factor is the ratio of true power to apparent power. So, PF is the ratio of true power What does P stand for? It stands for watts. You can't see that, but it stands for watts to apparent power. That is VA.